The global trajectory of the iGaming industry is increasingly defined by the transition from saturated mature markets to the high-growth frontiers of Latin America, Sub-Saharan Africa, and Southeast Asia. As of 2025, the Asia-Pacific region alone represents more than 43% of global smartphone shipments. Yet the technical environment in these regions remains fundamentally distinct from the Western development paradigm. The explosive growth in these emerging economies is underpinned by a massive global mobile user base exceeding 3.2 billion gamers. But this opportunity is gated by significant hardware constraints. Most international developers continue to build for high-end flagship devices, effectively ignoring the reality that the majority of the global market operates on low to mid-tier Android hardware with restricted memory, aging GPU architectures, and thermal limits that can terminate applications in seconds. To dominate these markets, developers must adopt a hardware-conscious engineering philosophy from the project's inception. The primary failure of many Western iGaming products in emerging markets is the assumption of hardware homogeneity. While a developer may test on an iPhone 15 or Galaxy S24, the target user in Brazil, Nigeria, or Indonesia is likely utilizing a device with 2 gigabytes to 4 gigabytes of RAM and a processor released several years ago. The smartphone market size is projected to reach $1,129 billion by 2034, but the vast majority of this growth is in the budget segment where hardware bottlenecks are the norm. In markets such as Nigeria and Brazil, nearly half of all active mobile devices possess 2 gigabytes of RAM or less. Memory is not a renewable resource. On a $100 Android device, the operating system and background services such as WhatsApp or System UI often consume 60% to 70% of available RAM. This leaves a narrow window for gaming applications. When an application attempts to allocate more memory than the Android system can provide, the low memory killer immediately terminates the process to maintain system stability. The data provided in the table above illustrates a stark reality. In India, Nigeria, and Colombia, more than 25% of the market is still operating on 1 gigabyte RAM devices. For a slot or crash game to be considered awesome in these regions, it must function flawlessly within these bounds. Modern iGaming pipelines that rely on unoptimized assets or massive JavaScript bundles will fail instantly in these environments. The storage war further complicates this. Users with 16 gigabytes or 32 gigabytes of total storage are highly selective about which apps they keep. If a game requires a 1 gigabyte download, it is competing directly with essential storage for photos and communication apps. Emerging markets are often geographically located in warmer climates, which significantly impacts device performance. Mobile GPUs such as the ARM Mali G71 or Qualcomm Adreno 506 are designed with aggressive thermal mitigation strategies. As the device temperature rises due to sustained computational load, the system triggers thermal throttling, reducing the clock frequency of the CPU and GPU to prevent hardware damage. Thermal throttling manifests as jank or dropped frames. In a high-stakes crash game, where the multiplier increases in real time and requires split-second timing for a cash-out, a sudden drop from 60 frames per second to 15 frames per second due to overheating is perceived by the player as a system failure or a rigged outcome. The Android framework provides a thermal HAL, hardware abstraction layer, that sends notifications to apps when the device enters various stages of thermal stress. A hardware-conscious developer monitors these statuses and dynamically scales back non-essential effects, such as particle density or post-processing, to maintain a consistent frame rate and extend the gaming session length. The infrastructure in emerging markets is characterized by high latency, frequent packet loss, and high data costs relative to income. While the price of 1 gigabyte of mobile data has decreased globally, it remains a significant barrier. In Nigeria, 1 gigabyte of data costs approximately 39 cents, while in Israel it is as low as 2 cents. Games must be designed to handle spotty connections. This requires a shift from constant server-side validation for every visual frame to a more robust client-side prediction model. In real-time multiplayer scenarios like crash games, synchronization is paramount. A delay of 100 milliseconds can lead to a ghost cash-out where the player believes they stopped the multiplier at 2.5 times, but the server recorded a crash at 2.4 times. The most critical technical realization for high-performance mobile development is understanding the difference between disk compression and VRAM usage. A common mistake among developers is optimizing for small file sizes using PNG or WebP and assuming that the game is lightweight. This is an illusion that frequently leads to crashes on low-end hardware. PNG, JPEG, and WebP are transmission formats. They are designed to save space on a hard drive or over a network. However, GPUs cannot natively process these formats. When the game engine loads a 500 kilobyte WebP image, the CPU must decompress it into a raw bitmap format, typically RGBA48, before it is sent to the GPU memory. A standard 4K texture with 4 bytes per pixel occupies exactly 64 megabytes of VRAM once decompressed. The math is simple but devastating. To calculate the VRAM needed for an image, we look at 3 main factors: width, height, and bytes per pixel. 4,096 times by 4,096 times 4 equals over 67 million bytes. That's exactly 64 megabytes of video memory for just one high-resolution image. If a slot game has 5 high-resolution symbols on screen, the memory usage can explode to over 300 megabytes instantly. On a device with 2 gigabytes of total RAM, where the OS is already under pressure, this memory spike is sufficient to trigger an immediate application crash. This is why many polished Western games fail to even boot on budget devices in Brazil or Indonesia. At Wizards, my game development studio, we solved the VRAM trap by leveraging GPU-native compression formats to maximize performance and efficiency. Unlike WebP, formats like KTX 2.0 and Basis Universal allow the data to stay compressed in the VRAM. These formats use super compression technologies such as ETC1S and UASTC. ETC1S offers the smallest possible transmission and GPU memory footprint, achieving 70% to 90% memory savings compared to uncompressed bitmaps. It is ideal for UI elements and non-PBR textures. UASTC provides higher visual quality for high contrast details, making it suitable for normal maps and complex slot graphics while still offering significant memory savings over raw formats. By switching to a KTX 2/Basis pipeline, a game's total VRAM footprint can be cut by 70% or more. This prevents memory crashes, allows for faster loading times as less data is transferred across the bus, and enables higher quality visuals on the same constrained hardware. The choice of development engine is the third pillar of hardware-conscious design. Engines that carry legacy overhead or were built for desktop environments are unsuitable for the $100 Android reality. Phaser 4 represents a fundamental shift in web-based game development by prioritizing a modular, performance-first architecture. Phaser 4 is architected to be massively modular. In previous versions of web engines, the entire core was often loaded as a single monolithic file. Phaser 4 utilizes ES modules and a TypeScript-first approach, allowing for tree shaking. This means that if a game does not use a specific feature, such as complex physics or 3D meshes, that code is not included in the final production bundle. This keeps the initial payload size small, addressing the storage war and reducing the data cost for the end user. Furthermore, the engine is designed to bypass the document object model entirely for rendering. By talking directly to WebGL and eventually WebGPU, the engine reduces the CPU overhead associated with the browser's layout engine. On low-end mobile GPUs, draw calls are the primary performance killer. Every time the CPU tells the GPU to draw an object, there is a substantial overhead. On a desktop, 500 draw calls per frame might be trivial. On a Mali G71, it is catastrophic. Ultra-performant pipelines utilize aggressive batching and texture atlasing. Texture atlasing involves combining many smaller images into a single large texture. This allows the renderer to draw thousands of sprites in a single draw call because they all share the same texture state. Phaser 4 utilizes an overhauled batching system that detects identical shader usage and groups objects together, minimizing the flushing of GPU batches. Mobile GPUs utilize tile-based rendering, which is highly sensitive to shader complexity. Developers must avoid expensive math and fragment shaders, such as trigonometric functions or logarithmic operations, which consume many cycles per pixel. Here are 3 tips we implement at Wizards that you can use to optimize your smart shaders and GPU performance. First, avoid branching. Using if and else statements in GLSL code is particularly expensive on older mobile chips because the hardware often executes both branches and discards the unused one, wasting cycles. Second one, bake textures over dynamic lighting. Real-time lighting is a luxury that emerging market devices cannot afford. Developers should use baked textures where highlights and shadows are pre-calculated and stored in a light map texture. This creates the illusion of 3D depth without the runtime cost of calculating photons for every pixel. Third one and last one, vertex color manipulation. Instead of complex fragment shaders to handle color shifts, developers can use vertex color manipulation, which is mathematically cheaper and processed far less frequently, once per vertex instead of once per pixel. Crash games and real-time multiplayer titles require a level of synchronization that most slot games do not. The gameplay hinges on the accuracy of the multiplier and the timing of the player's exit. In crash games, the multiplier increases at an exponential rate until a random crash event occurs. Because real money is involved, the trust chain between the server and the client must be unbreakable. If the client lags by 200 milliseconds, the player might see a 2.0 multiplier and click cash out, only to find the server had already crashed at 1.85. To maintain this trust, developers must optimize TCP IP traffic, minimize lag even under high concurrency through the use of WebSockets instead of HTTP polling, adopt scalable message queues, see event-driven architectures that prioritize time-sensitive actions with sub-millisecond responsiveness, edge computing, deploy game servers as close to the target player base as possible in São Paulo for Brazil or Mumbai for India to reduce physical distance latency. Advanced synchronization often requires moving beyond standard protocols. The SINLAM Protocol is an example of a time-sensitive data management system designed for low-latency applications. It utilizes a low-overhead header that includes a temporal value to indicate priority, and a micro-synchronization timestamp with sub-microsecond precision. By prioritizing high TV packets like a cache-out command over low TV packets, like a non-essential chat message, the system ensures that critical game actions are processed first, even in congested network environments. Hardware consciousness is not just about avoiding crashes. It is about creating an experience that feels premium despite the limitations. Consistent frame delivery is more important than the absolute number of frames. A stable 30 frames per second is psychologically superior to a fluctuating 60 frames per second that frequently drops to 20 frames per second. High frame rates 60 plus are associated with lower input lag, approximately 16.7 milliseconds per frame at 60 frames per second, and increased player trust. In real money gambling, visual stutters are catastrophic. Players associate lag with foul play. If a dealer's hand in a live game skips a frame, the player's immersion is broken and their suspicion increases. Research on slot machines shows that immersion, or being in the machine zone, is highly dependent on continuous audiovisual cues. A hardware-conscious game maintains this immersion by ensuring that animations are predictable and fluid, even if the graphical detail must be lowered on budget devices. The economic reality of dominating emerging markets is driven by user acquisition costs and lifetime value. In markets like Brazil, revenue is growing but remains lower per user than in Tier 1 markets. Therefore, maximizing the return on investment requires extreme efficiency in user acquisition. Optimization directly impacts these numbers. A game that loads in 2 seconds instead of 10 seconds has significantly higher day 1 retention. A game that doesn't crash on 2 gigabyte devices has a much wider net for acquiring whales, the small group of high-spending players who drive the majority of revenue. By engineering for the hardware from the start, developers reduce their effective CPA because every paid install is more likely to result in a functional, retained user. We at Wizards apply certain recommendations to build high-performance iGaming applications for emerging markets, ensuring they adhere to a strict set of technical principles that prioritize hardware consciousness. Instead of a one-size-fits-all build, games should implement performance tiers based on device detection. Low tier disable dynamic shadows, limit particle emitters, use ETC1S textures, and force a 30 FPS cap to prevent thermal throttling. Mid-tier, 3 to 4 GB RAM, enable basic animations, use UASTC textures, and target 60 FPS with dynamic resolution scaling. High tier, 6 GB plus RAM, enable high-fidelity effects, MSAA, multi-sample anti-aliasing, and post-processing stacks for users with modern flagship devices. Developers often lose touch with the reality of their users because they work on high-end workstations. Organizations should mandate the use of a budget mode in debug builds. This mode should artificially throttle the CPU and GPU to match the clock speeds of a 2018-era chipset, limit available memory to 1.5 GB, simulate a 4G connection with 2% packet loss and 200 milliseconds latency. Disable hardware acceleration to reveal inefficiencies in the core logic. The transition to a KTX2-based pipeline must be enforced at the asset governance level. Artists should not be allowed to check in PNGs for production use. All textures should be automatically transcoded to Basis Universal Pipeline, ensuring that every asset is GPU ready from day one. Dominating the explosive growth markets of LATAM, Africa, and Asia is not a matter of graphical superiority, but of engineering discipline. The developers who succeed in these regions are those who treat a $100 Android device with the same respect as a high-end console. By breaking the VRAM trap, embracing modular engine architectures like Phaser 4, and implementing low-latency synchronization protocols, developers can deliver an awesome experience that feels premium regardless of the hardware. The future of global iGaming is mobile, but more importantly, it is optimized. Most of the games featured in this video were developed by Wizards. To learn more about our high-performance iGaming solutions, visit wizards.us.